welcome to the second video of this series of lectures. So, I thought that we discussed last time is the three approaches towards complex analysis. So I thought let me make that little more precise. Of course, this is all in the overview part, but will not prove things. But let us just mention things a little more precise way. So, suppose omega is a domain in C. Domain means open connected set. Open connected subset of C is called domain in C. So we consider a domain and consider a function from omega to C. Now there are three approaches. There are three approaches to complex analysis. Means the three approaches towards the functions there which forms the prime objects in complex analysis, namely holomorphic functions. Well, we'll come to that. So one, of course, that was due to Cauchy. F is said to be C differentiable or complex differentiable at A in omega if this limit f of A plus h minus fa by h as h tends to 0, note the limit at h should be in C. So you have, suppose this is a point A, and there are several directions from where it can come to the point A, when h can come to 0, so that h plus h comes to A. This limit exists, and f is said to be holomorphic. The term I was talking just few minutes back is said to be holomorphic on omega if f is C differentiable at A in omega for all A in omega. Well, C differentiable at every point in omega. Well, so these are the functions I was talking. Second approach was due to Riemann. So he assumes f omega to C is continuously differentiable, which means the first order partial derivatives are all continuous, and if f equal to u plus iv, Yeah, del u by del x equal to del v by del y, and del u by del y equal to minus del v by del x on whole of omega. So these two conditions, so will mean the same thing. So f is different, is holomorphic if it is continuously differentiable and this one. Alright? So yeah, one can define this one, but we'll go with the definition of holomorphic at this one, and of course we will show this, all these things are equivalent. Now the point is that you see this is a system of partial differential equation. Riemann's emphasis was these are what lies in the basic. So if you know the derivative at, let's say, any point A, and if you consider f to be u comma v from omega to R2, so omega you can think of a subset of R2, then d of A is this one, del u by del x at A, del u by del y at A, del v by del x at A, del v by del y at A. The point is, as you know, derivative for map from Rn to Rm, that derivative at a point is a linear map, real linear map. So this is a real linear map. But what makes this differential equation is this to be complex linear. So this system star makes df at A complex linear. Right, when viewed as a map from C to C. Right? So this was a real linear map, and what Riemann has imposed the partial differential equation, system of partial differential equations which make the derivative complex linear. But that's also very natural. If you look at map from Rn to Rm, you get a derivative as a R-linear transformation. You better expect here as a C-linear map. Alright? Okay. So look at the third one. Is due to Poisson space. F from omega to C is said to be complex analytic on omega if for every point A in omega there exists a power series summation A n z minus a for n in from 0 to infinity such that 1 the power series this radius of convergence are greater than 0 to, so which means this, you have a point A, this is A, and you have this is R. So in the base curve radius R, this makes sense, this converges uniformly and absolutely on uniformly on compact sets and absolutely on every point. Yeah, you can say that this series converges absolutely. We'll come to that convergence is very details. So it converges here, so it gives a function. And second is this fj has to match with this on omega intersection this disk mod z minus a less than r. Right? So the function matches on the intersection. So if this is the disk and intersection is omega is like that, this is omega, on this to match. On this two should match. So this several things have several implications. For example, you get C linearity from here, right from very beginning, and here you see that function is, once you have Pauli series, it is infinitely differentiable, right? So any functions with this property will have this. So all three are equivalent. Right. Yeah. So this was three approaches. We'll look at. We'll start with this one, basically, because it has some nice properties which is just analogous to what is in real variable. Of course, Cauchy's approach is also analogous to real variable. But we'll come to that along with this one, and we'll show these things are equivalent. But the equivalence of this and this, which is a little bit non-trivial, one need to first develop theory of integration. After that, one can do this equivalence. So this Pauli series is kind of very special. Just one's differentiability here would give you infinite differentiability, right? And that too a Pauli series. Once you know a Pauli series, you know the coefficient in terms of derivatives, and you know a lot of stuff from here. All right. So that's actually a brief. Three approaches. That this is little more precise version of the three approaches which I talked last time. Right. So we'll start the real course with proof and the stuff. From next time onward, we'll look at first this Pauli series over R, which is very easy to understand. Everybody knows real analysis. Now I think everybody is very comfortable with it. So we look at Pauli series, study Pauli series over R, the real variable, and we'll see the same proof, just analogous to it. Putting x to z just like that actually gives us a lot of properties for this Pauli series, for holomorphic complex analytic function. Okay, stay tuned.